Okay, I would say let's start our workshop. Welcome everyone. Good morning, good afternoon, and good evening. And welcome everyone in the BRAINE online workshop. First of all, let me introduce ourselves. And this is the program of the workshop. My name is Peter Santo from Budapest University of Technology. I will be the host. And the first presentation will be presented by Brad Buining from Edge MicroDataCenters, then Sean Ahern from Dell. Then we have a short break and continue with the hardware part presented by János Lazányi from PCB Design and Brad Buining from Edge MicroDataCenters. Then I will present the acceleration part of the hardware architecture. Then again, we will have a short break and continue with the second software part presented by Javad Shamanara from Leibniz University. We plan to have a question and answer part of the workshop at the end. So please write down your questions or write them into the Q&A panel, and we will answer at the end of the workshop. Now I will give the screen sharing to Fred, and he can start his presentation, so I stop sharing.
Thank you, Peter. Let me just screen share. Here we are. And here we are. The BRAINE project. We are 8 months into a 3-year, 16 million project, of which 8 million is EU funding and national co-funded. It's a highly complex project, looking holistically at all the aspects of creating an intelligent edge infrastructure. It would be pretentious to think we find all the answers today on the next 3 years, but we do hope that through our presentations and work, we inspire you to join us and develop some of the answers as well. There is still much work to do. My presentation will explain what the BRAINE project is aiming for, and follow-up presentations will dive deeper into software and hardware architectures, the requirements, and some of the capabilities. The internet infrastructure is expanding, creating more interconnections at the core, the regional, and the metro area, connecting to every part and vertical in our society. At the edge, sensors and devices digitally transform our world into data, big data, data that is growing at 61% year after year. And did you know that health data accounts for 30% of that growth? Producing big data is not a mission in itself. We expect to draw value from analyzing that big data. In data-dense areas, the amount of data and the required analytics will accumulate, from a simple chat box to apps on phones and smartwatches, inspection drones, robots in factories, and sensors in large, complex systems. For example, an airport will need to ingest an average of 500 gigabytes of data from each aircraft, process all the travelers' data, support the autonomous taxiing of airplanes, the automated handling of luggage and cargo, etc., and etc., all at high speed and with little to no latency. A factory of General Electric in New York is equipped with over 10,000 sensors linked to all the other global factories around the world. And they all report on the manufacturing process and building conditions. Employees can view the data, receive alerts of production deviations, and improve the quality and the overall process as it happens in real time. Until 5 years ago, industry believed that all the AI analytics on edge data could run on a cloud infrastructure separated from the edge. Progressive insight shows us that this will not be an option for a growing number of applications for a number of reasons. The unpredictable latency of the unintelligent network, reliability of the network, costs of transporting the data, privacy of data, protection of data against data theft or leakage of the analytics outcome through metadata. For a growing number of applications, the cloud is not an option. Not today and not tomorrow. When you look at the data and how much interference and training for AI is required, the numbers are incredible. For the data center market, we are looking at 9 to 10 billion until 2025 in terms of inferencing, and the training up to 5 billion. But at the same time, we see that the edge is also coming. Until 5 years ago, we didn't see that data appearing, but now the edge is an option. An autonomous edge, where edge native cloud microdata-centers run some of the workloads that normally would run in a cloud data center. We are not the only one with that vision. A recent 6G white paper gives us an interesting and comprehensive perspective on how far the development of an edge intelligence should go. It requires more than just a powerful gateway. It requires an edge infrastructure at the intersection of edge and intelligent device, a powerful infrastructure with edge software and a platform for orchestration, where we can have real-time and online learning and distributed training. A platform that aligns with end-user context of locality and data placement, that provides security and privacy to our data and to our infrastructure, but at the same time allows us to share that infrastructure and share some of that data and capitalize on it. 18 months ago, we wrote the BRAINE project outline with a similar holistic perspective on edge intelligence. We founded a consortium who shared that view and had the interest of developing such a platform and tested within the context of 4 use cases: healthcare, manufacturing, smart city, and robotics. The BRAINE consortium looks across the whole solution of edge intelligence infrastructure. And among many questions, these are some of the questions we would like to answer. How to trust edge devices? What ways can we use to identify and authenticate them? How can we implement quantum-proof encryption technologies to protect against malicious attacks? Network intelligence. Where and how can we apply AI to manage the network, to manage the capacity of the microdata centers, require a reliable connectivity? And especially as the edge infrastructure grows, it needs to be automated and efficient. We look at giving data ownership and what that does mean. What does sovereignty mean? How can we enable people to own their data, be able to decide on how others can use it, where it is stored, and to what extent it is used? For all that, we need to be able to trace the data throughout the network. And looking at edge data center hardware, it should be able to be implemented and embedded in the edge. So it should be able to function outside of the conditioned environment of regular data centers. It should be energy efficient, compact and small, but also fault tolerant and full composable to meet end user needs. The Edge cloud stack is different from a hyperscale stack, since the Edge infrastructure consists of independent distributed microdata centers that are anonymous, yet can decide to be part of a federation and collaborate. We need distributed intelligence in the infrastructure to make that work. And it also is a challenge to data storage. How can we store the data resiliently in the autonomous and distributed yet federated infrastructure? This is another question we would like to answer. And towards the end of the project, we also need to think about, so what are some of the services that can be offered on such an infrastructure? Since it is decentralized infrastructure, the services and the infrastructure will be owned by many different players. There's no centralization. Let me use a picture of a smart hospital as an example to explain some of the advantages of this distributed infrastructure. But be aware, this infrastructure is not only applicable in the smart hospital. It can be rolled out over a smart city, a smart factory, an airport, a seaport. We've been discussing in New Zealand how such an infrastructure could be rolled out over the complete dairy industry, farms and factories. The advantages of such an infrastructure we would like to highlight are data and AI ownership, elasticity and endless scalability, CapEx and OpEx savings, and resilience and fault tolerance. Looking at data and AI ownership, an edge native cloud is built from a mesh of microdata centers embedded in the edge. Privately owned edge and cloud gives you complete ownership of all aspects of your data that otherwise could become exposed to external infrastructure and service providers in an off-premise cloud. The raw data, the aggregated data, the analytic outcome, and any piece of meta information is yours. It stays on-premise, is protected and securely encrypted. And the same goes for your AI model. Now that you have complete ownership, you can create alliances in your supply chain with your peers to exchange data in a privacy-preserving and GDPR-compliant way. It allows you to create alliances where you can do federated learning and gives you access to large numbers of data to train your AI. It is something that is also in line with the European strategy of creating a single market for data with clear rules on data access and reuse, GDPR compliant, building a European cloud capacity such as Gaia-X. When we look at elasticity and endless scalability, bursts of data and spiking workloads are absorbed firstly by individual microdata centers. Secondly, through groups of microdata centers working in federation. And in emergency situations, workloads can be redirected to a metro data center. Intelligence on the infrastructure will orchestrate within the boundaries, yet set by various federations and indicate when structural addition of servers or microdata centers are needed. Virtualization, Docker, cloud-neutral container orchestration tools like Kubernetes guarantee transferability of applications and data. When we look at CAPEX and OPEX savings, there are a number of things that we are implementing. The intelligence built into the infrastructure optimizes the use of the network bandwidth and the MDC capacity. It keeps data and applications close to the end user. Data sharing is also in your hands, including the AI models. So you can start capitalizing on that ownership. You can also offer, when available, some of your servers of microdata centers and implement some kind of multi-tenancy and charge for it. The infrastructure design in itself is very energy efficient. We use small form factors with power efficient systems on chips. We do almost fully passive cooling, saving 30% on your energy bill. And we capture 97% of the server heat that you can reuse for facility heating. The distributed microdata centers can easily be connected to a microgrid of renewables, of wind and solar. There is not much implementation needed into the building. You don't need to create a special place, a server space. You don't need to make adaptations to your power grid or your power distribution. Microdata centers are small, have a small footprint and a small power draw. And last, resilience and fault tolerance. A cluster on a microdata center and federations of microdata centers reduce the threat from single point of failures. AI using information from the servers and switches optimize utilization in the distributed infrastructure across the various federations. The switches and the smart NICs collaborate for offloading some of the networking loads from the CPU, but they also run anomaly detection in the connections and data streams. The platform itself, of course, will manage applications recovery. And did you know that solid-state hardware has a 10 times lower failure rate than regular air-cooled data center hardware? Those were some of the advantages of the BRAINE infrastructure that we tried to build. Still, quite a few organizations don't know where to start with building their own infrastructure for big data and AI. We hope the BRAINE project outcome lowers this threshold. We have a few other recommendations. The edge intelligence has just started to emerge. Nobody knows exactly how the edge infrastructure will materialize. Therefore, focus on the potential, ownership of your data and AI model, and on the long term, start building early, gradually, but never finish. Because we can expect more integrative projects for edge intelligence, such as BRAINE, and we can expect also more guidance, legislation, and financial support for building edge intelligence. And some of that support will come from the EU. The BRAINE project. So the following presentations after this one will look a little bit deeper into the hardware, the heterogeneity, the mix and match of CPU, GPU, FPGA, and NVMe, scaling and density from small microdatas, 1.5 kilowatts, to larger ones, of 5 kilowatts, but all in a 3U chassis. And we can even scale larger. We will look at the energy efficient cooling, and we'll explain a little bit more about the dual switching layer of PCIe and Ethernet switching. There will be a presentation on acceleration. Why do we use and choose the Xilinx Versal FPGA and the NVIDIA Xavier GPU? What are they capable of? And finally, we will also start presenting some of the architecture, the SLA broker, federation and work placement, and telemetry and federated learning. After today, the HiPEAC conference, we will have more discussions the coming years. And this year, we'll have a few online discussion panels. In the end of January, we will talk and discuss telemetry and monitoring at the edge, the 28th of January. In March, we will look at AI and edge computing. And May, we will have a look at multi-level federated edge. In July, join us to look at edge computing hardware. We'll give you an overview and a roadmap into the future. And in September, we'll discuss BRAINE and the semantic web. And our panel discussions will finalize in November with a panel on quantum key distribution technology in fiber-based connectivity links for edge nodes. This is the consortium of the BRAINE project, and we hope that we will be talking to you more in the future. Thank you for your attention. Back to you, Peter.
Thank you, Fred. Now I will give the screen sharing to Sean, who will present the first part of our software architecture. Sean?
Yep, thank you, Peter.
Fred, you may have to stop sharing your screen.
Let me see. I'll be back in a minute. Yep.
Okay, can everybody see that?
Yes.
Okay, thank you. One moment. Excuse me, one moment. Just need to start sharing my camera, sorry. Okay, hi everybody. My name is Sean O'Hearn. I am a research scientist for Dell EMC. I need to start my presentation again. Sorry, I seem to have 100 applications open. Okay, sorry. Can everybody see that now?
Yeah, it's okay.
Okay, thank you. Sorry. So yes, my name is Sean O'Hearn. I'm a research scientist at Dell EMC. I'm the technical coordinator for the BRAINE project. So I'm here today to talk to you about software for an autonomous and fully distributed edge native cloud, i.e. the BRAINE platform architecture and software. So my role as the technical coordinator is to oversee the development of the BRAINE platform as a whole. As you can imagine, with a project with 27 partners from 14 countries, with I would say the majority of those partners developing at least one software component, it's good to have a technical coordinator to oversee the integration of all these components into a unified architecture. With me, I've also got Javad Chamanara, who will be speaking on various other architectural aspects. Excuse me. If you've got any questions that aren't answered in the panel session, please feel free to reach out to either of us at our respective emails. So just quickly letting people know the structure of this. So I'll be speaking for the first 30 minutes. I'll be speaking about the platform architecture as a whole, followed by the global file system, several BRAINE architecture components such as the global file system, distributed knowledge base, and SLA broker. Then Javad will be speaking in the second time slot about the federation model used to build independent edge data centers, followed by an in-depth look at some other important software aspects of the project, namely the telemetry system and the use of AI for federated learning, and in other aspects as well. So then, moving right into the platform architecture. So as already mentioned, the BRAINE project is a large project covering a lot of ground in both hardware and software. One of the key goals in BRAINE is to develop independent edge microdata-centers. So designing a software architecture to support this has a number of new and interesting challenges. Previously, relatively simple things such as, say, the locality of data are given new paradigms to consider when approaching the problem with the vision of an independent autonomous edge. Data ownership considerations are of high importance in this type of approach, as various aspects such as the security, privacy, and access of an owner's data on an Edge MicroDataCenter, EMDC, must be very well defined with the use of policies and other protections, particularly when the time comes for that data to be processed or consumed by perhaps another third-party service on the EMDC, or if the data owner wishes for their service and data to be transferred to another Edge MicroDataCenter owned by a third party, perhaps. Similarly, resilience is an important consideration in this type of architecture, as data should be replicated across nodes within the Edge MicroDataCenter and also across other Edge MicroDataCenters for resilience and availability. But this process has to be done, of course, with consideration given to the defined data policies or any data regulations that might exist. So BRAINE is focusing on 4 use cases that you can see in this diagram. The first use case 1 is the intelligent hospital. Use case 2 is the intelligent city. Use case 3 is robotics and Industry 4.0. And use case 4 is supply chain. I'll go into a bit more detail about the first 2 use cases later on and how they exploit the architecture that we're developing in this project. So then, starting with the front end of our platform architecture. So we have a user interacting with the platform represented here at the very top, who connects to a web UI and an authoring tool. So the purpose of the web UI and the authoring tool is to present the user with a list of services which can run on the BRAINE platform. So that connects to a service management component, which has a catalog of all the services that are available to be run on the platform. Future revisions will allow users to install their own service images if desired later on. So when choosing a service to run, if that service consumes or produces any data, the user can define data management policies to restrict and control how that data can be used on the platform as they see fit. The service management components consist of a service repository and catalog containing images of all the services available that can be run on the platform, a service registry which maintains an active list of all services currently running on the platform, a service manager which instantiates and terminates services and images on the platform, and a resource manager which manages the resource usage of the services running on the platform. By platform, I should perhaps mention that on kind of the services that run for the use case and the users run on what's called we'll call a Kubernetes worker load, which I'll explain later. For data management, there is the data placement framework, which works with the defined policies to ensure data locality, privacy, and security, and also works with the workload placement framework, which I'll show in a minute, to ensure that the worker services that are processing incoming edge data aren't placed remotely from the source of that data, which would reduce performance, for example. The distributed knowledge base is used as a data store to collect metadata on active policies, running services, and available resources, providing an API for other components to access that data to perform their tasks, which I'll explain later. Moving further into the architecture, you can now see the entire BRAINE platform abstraction framework, or perhaps management framework would be another term to use. As previously mentioned, we have the workload placement here in the center, which operates and maintains Kubernetes worker clusters for running use case applications. This component integrates heavily with all the other components in the platform and will operate as a Kubernetes federation, which Javad will explain later on. Other components include the monitoring system, which contains any data policies, rule violation events, security events, and so on. This works with the data integration platform, which will be used to collect and collate logging and monitoring information to be integrated with an immutable logging or blockchain system in the future. The SLA broker is a service level agreement broker, is used to monitor and enforce any service level agreements created when a user instantiates a service. It will monitor the resource usage of the entire Edge MicroDataCenter to ensure that each service is getting the correct level of resources, and will act upon the workload placement framework if it detects a violation. The SD controller and network analyzer are used to manage the 5G infrastructure that sits between the Edge MicroDataCenter and Edge devices, which I will show you now as we move further down. So now moving further down, we have the worker nodes as described here, which are the Kubernetes worker nodes managed by the workload placement framework. The use case applications run the services that have been defined in the service catalog here, and they are the global file system and data management is defined for them in the data management framework above. So as mentioned, here you've got the 5G infrastructure, which is controlled by the SD controller. This is used to improve the performance of the incoming data store, the incoming data coming from the data sources, which will depend on the specific use case. So then, if we zoom out and look at everything as a whole, everything I've just explained before the 5G infrastructure all sits inside a single Edge MicroDataCenter. So we use two different types of Kubernetes clusters in this architecture. We use one Kubernetes cluster just to deal with management, which is the Kubernetes management cluster highlighted here in blue. And then you've got the Kubernetes worker cluster highlighted in green. So now I'll talk a little bit about the use cases. So use case one, as I mentioned, is smart hospitals. One of the use case application workloads that would run on the Kubernetes worker node for this type of use case is a time series sensor data processing. So that's information such as a heart rate from a sensor on a patient. This type of data, of course, is highly restricted and subject to strict regulations. So the example of the challenges that you would face in this type of use case with this type of architecture, for example, are what happens when a patient moves from hospital A to hospital B, and both EMDCs could be owned by a third party, or are just operating as independent units. So for this example, for this type of architecture to work, there's a number of things that are required. The first thing you require is some sort of federation to allow the workload that was processing the time series data and to allow the workload that's processing time series data to move from EMDC A to EMDC B. You'll need a service mesh in case that particular service or that service image wasn't in the other EMDC service catalog, so it needs to be transferred in such a way that it can be quickly instantiated before the patient arrives at the next hospital. And of course, if the other hospital is not owned by the same company, it's a third party, there needs to be the correct regulations in place to ensure that both the workload and of course the data, as I'll explain, are transferred in a compliant manner. Then of course you've got the data requirements. So for this type of architecture to work, you need some sort of global file system. You'll need to make sure, of course, as mentioned, this type of data is highly restricted, so it's going to need, so the policies and the regulations for that type of data need to be ensured compliance needs to be ensured for them. And then, of course, you've got data requirements in terms of redundancy and resilience. So if you're, for example, replicating this type of data for resilience purposes, given that it's highly restricted, it may not always be able to be replicated to every EMDC. There might only be certain EMDCs in certain locations that are permitted to replicate the data for resilience and availability purposes. The second use case then is smart cities. So for this workload, we've got GPU accelerated video processing. I think we've also got some other hardware acceleration using FPGAs. For this type of data, it has less restrictions on it in comparison to, say, medical data, but it's got a number of different states, such as raw and anonymized. So the example for that is traffic analysis. So this is where you have a number of video feeds coming into your Edge MicroDataCenter. They might be, say, from a street. So on that street, the camera might have pedestrians, and it might have license plate numbers on the vehicles. Depending on your application, this type of information might need to be anonymized before it can be processed by a subsequent service. So that's how you get multiple different states of this data, raw or anonymized. So for this type of workload, the requirements are it will need to be a cross-platform architecture. The reason for this is, as will be explained later in the hardware presentation, we have a number of x86 nodes, and we'll have a number of ARM nodes which contain GPUs. So it's important for the workload placement framework and the container architecture to support deploying this type of workload on either an x86 machine or an ARM machine. Similarly, the workload placement framework and the kernel that's running on top of the Edge MicroDataCenter needs to support hardware acceleration, of course, and it will need to support the concept of a multi-tenant environment, which is where multiple different services from multiple different parties might be consuming the same data source or same process data output even. For data requirements, you need a file system that supports write-once, read-many approach because of this multi-tenant environment. You'll need to have a system in place that can suitably protect the raw data for compliance and security purposes. And you'll also need a file system that can support, again, multiple different processes from perhaps multiple different parties, all accessing perhaps one process data source. So if we move away from that and we come back to our architecture discussion, so as I mentioned previously, when we zoom out, as we see here, we have all of our components in a single scope, in a single EMDC, but what do we do when we want to scale beyond a single EMDC? So the traditional approach would be to centralize a number of your management framework components. So in this case, this is the traditional approach that hyperscalers would use when they deploy edge environments. You'll have a number of your management components centralized in the cloud somewhere, managing a number of edge devices. They'll communicate to their edge devices with the North-South API, and they might move workloads across the edge with an east-west communication. So we don't want to do that. What we're trying to do is to have each EMDC operate as an independent unit as part of a federation. So as you can see here, this is similar to the previous diagrams I've showed, where you've got the Kubernetes management cluster and all of the management framework components inside it, all running inside a single EMDC. And each EMDC can operate independently, but they can still communicate with each other in a federation to move workloads and data across as necessary. This is just another view of what that might look like with the previous architecture diagram. So you've got your Kubernetes federation moving workloads across from one EMDC to another, using the service mesh to maintain the correct service repositories between both EMDCs to make sure they they can the services for the use case applications can operate with each other or operate in GMDC. So that's finished with the architecture, and now I'm moving on to the software components. So first up is the file system. So when considering the requirements for the file system, for this platform and for this project, there's two major types of data to consider. So first is the container state data. So this is the data that's being used by a worker service running on a worker node. It'll most usually be small files which are frequently accessed and are required for certain use case applications. The example of that would be a database. A database for a use case application might be frequently accessed, and we need a file system that can support that. The second type of data then would be the use case application data, which would be larger files which are less frequently accessed and may need to be archived. So the example for that would be large amounts of processed or archived video data. In the case of the example for the hospital use case, once the time series data is collected in large blocks and is then eventually archived after a certain length of time, which would count as use case application data in this sense. But while the time series data is being processed, it would be considered container state data. So as such, we need a file system which can satisfy these requirements. So we need a global file system which supports low latency access to container state data for both the performance of the application and also for workload movement. We need efficient management of large volumes of use case data. And we need the flexibility to create and enforce data policies such as data placement locations and access. So our choice for this is Apache Ozone. It's a distributed global storage system maintained by Apache and released in September last year. It uses an evolution of HDFS called HDDS, which could be considered entirely its own new separate system. So the pros about this system is it's an object, block, and file storage system. It's got native integration with Kubernetes, which we need for this project. It's highly compatible. It's got APIs for HDFS, Amazon S3, NFS, and more. And it supports the concept of location-based data placement. So cons would be that it's relatively recent and that it's got a centralized management hierarchy. What that means for us is that while it is traditionally designed to be used in a centralized management model, all this simply means is that the central manager will be run individually on each EMDC inside the management framework, and then each of those central managers will communicate with each other to make sure or to ensure the global file system remains intact and data can still be moved between EMDCs. Other file systems that we investigated were we started with HDFS, which is the traditional Hadoop file system. It works well for large amounts of data, but it doesn't work very well for container state data. So we decided not to use that. We've also investigated Ceph, which is a very powerful distributed global file system. It works very well for edge-based architectures. However, it uses an algorithm called Crush, and that algorithm is very effective at distributing data across the global file system effectively, but it isn't very easy to modify to support the concept of location-based data policies. So we also looked at ClusterFS, which also works very well and is a fully distributed file system for Edge, but it has comparatively higher latency than Ceph or Ozone. So in that sense, and because of that, as a consequence of that, it doesn't perform very well for real-time applications, such as the video processing use case. And we also looked at IPFS, which again, on paper, is a very effective distributed file system. However, it can be quite inefficient when it scales up when searching for searching for files, and from investigations done on previous projects, we found that it usually doesn't perform as well as expected. So that's why we chose Ozone. Moving on, then we've got another component, the distributed knowledge base. So as I mentioned previously, distributed knowledge base is designed to collect various different metadata, information, such as information on the Kubernetes cluster, the network nodes and switches, the EMDC hardware, memory, CPU, storage, etc. It collects all this data. It uses a messaging service to handle these incoming feeds in real time and at scale, and it ingests it to make available for the workload placement framework and other components, such as the SLA broker. Apache Kafka is used for this with multiple brokers for fault tolerance. And then for long-term storage, we're using HTTS or Ozone. So it's a reliable and cost-effective access to historic resource information, and all data on it will be encrypted in transit and at rest. So this is the architecture for the distributed knowledge base. So on each EMDC, you'll have the Kubernetes worker clusters with the metrics server collecting information about the worker nodes and how they're performing, and the resources, etc. This will be collected into Kafka and the Apache Ozone file system. It'll store all that data onto HTTS, and then it'll replicate that data across multiple different EMDCs. The purpose, one of the advantages of doing this, for example, is when you can replicate it across multiple different EMDCs, then each EMDC can quickly check the state of the other EMDC without having to, without the latency penalty of having to communicate with it to determine its resources. It'll already know from the replicated distributed knowledge base if, for example, there's enough resources to move this workload from EMDC1 to EMDC2. So the final component I'll speak about is the SLA broker. The SLA broker, as I mentioned, service level agreement. It's for policy monitoring and control. That's for service level agreement policies, and can also be used to enforce data policies if required. So it'll primarily influence workload scheduling and the workload placement framework. It'll monitor services on a per workload basis. It'll analyze the standard serverless level agreement metrics such as CPU utilization, availability, and bandwidth. And then for enforcement, it'll maintain a list of defined policies and actions in real time. And of course, it'll be directly integrated with the workload management framework. So when creating the SLA broker, there's a few architectural considerations to be considered when we go for a centralized model or a distributed model, as I discussed previously. So for the SLA broker, a centralized model would require extensive data filtering to be scalable, because it would be collecting the information from, say, a large number of EMDCs in a location rather than just maintaining its own EMDC. And as such, the reliability of the broker depends on how efficient that filtering mechanism is that you develop. And even if you run it in a centralized manner, you would still need some basic brokering tests still run at the edge for latency purposes. So for the distributed approach, where it all runs independently on each EMDC, it will require more resources on the edge, which could impact performance, as you might expect from other components in the architecture too. But as a benefit, it's less dependent on the filtering mechanisms. It's got a much faster response time. But another thing to consider is that you will have to have two different type of instances, one for managing the local EMDC and one for communicating with other EMDCs. So how that might look in terms of an architectural point of view. So on the centralized one, you can see here the abstracted framework management components here are running in the cloud. So, they're running somewhere remote from the EMDC. The SLA broker is running, collecting data from multiple different Edge EMDCs, which has to be collated in this data service API and then collected into the inventory manager and then monitored by multiple different policy managers. So in the distributed architecture, you've got all of this is running all inside a single EMDC, whereas just this piece was running inside the EMDC in the centralized approach. So here, you still have a number of different policy managers. You still maintain an inventory. It still speaks to the workload and data placement frameworks, but as I said, it's running on the Edge MicroDataCenter, and so then it still maintains local policy managers. It still maintains local policy managers, but it doesn't have to collect as much data as the centralized model, so it can operate much quicker. So for the structure of the SLA broker, the inventory system is SQLite. The SLA broker speaks to the inventory system via the Flask and Alchemy APIs. The SLA broker speaks to the northbound, which would be the workload placement framework or the data placement framework via REST API. And the SLA broker can speak to the other components such as the analyzer and the policy manager via Kubernetes. So in summary then, as I mentioned, one of the main visions of this project is to create an architecture that supports the concept of independent Edge MicroDataCenters. So as you've seen there, we have a number of requirements in terms of locality, autonomy, ownership, privacy, resilience that all need to be, all requirements that need to be met, and they all have a number of challenges that need to be overcome to support this type of architecture. So some of those challenges that we're developing solutions for are, of course, the federation model, which, as I mentioned, Javad will speak about later on. The choice to go for distributed management architecture versus a centralized management architecture, and of course, one of the key components and one of the key features in this type of architecture is the dynamic movement of services and data across multiple Edge MicroDataCenters. It's a very complex problem. I can't promise that we know all of the answers yet, but I think it's a very interesting challenge and one that we hope to overcome in the project. And that's everything from me. Thank you very much. Back to you, Peter.
Thank you, Sean, for your presentation. It was very interesting, at least for me. I hope all the attendees also found it interesting. Can you please stop your screen sharing?
Oh, sorry, I thought I did.
No, never mind.
How do I'll just do this for a second.
Okay.
Oh yeah, sorry. I see it there. Sorry.
Okay, now we will have a coffee break, and afterwards we will continue with the second. Oh, I didn't share my screen. So after a short break, we will continue with our second session, which will detail the hardware architecture of the EMDC. So we will continue at 10:40. In the meantime, please enjoy your coffee. Okay, let's continue with the second session. As I mentioned, the first presentation will be held by János Lazányi. So I would like to ask János to start his presentation. János, please.
So actually, it's not absolutely correct. Fred will give a general overlook, and after that, I will continue with the deep diving in the details. So please
okay.
give it to Fred.
Then, Fred, please start.
Thank you, János. Thank you, Peter. Let me screen share. Oops. There we go. Share screen. Come back to PowerPoint. So I think since, from what we've told you so far about the intelligent edge, you can imagine there's going to be a lot of interactivity at the edge. We talk about a lot of small sensors and devices interacting with the edge infrastructure, pushing data, but at the same time requesting some processing or some intelligence from the data that's being processed. That interactivity demands also a lot of bandwidth. Regarding the heterogeneity of the data streams, it can be video, it can be sound, it can be just sensor information. We need also a lot of heterogeneity in the microdata center itself, but also a lot of autonomy, not autonomy only on the microdata center level, but also on the server node level within the microdata center. So one of the reasons why we have set up the infrastructure as we're going to present it to you now is that to facilitate a lot of interaction at the edge. So to dive a little bit deeper into the architecture, our smallest building block is a building block of 8 nodes, supported by a dual switching layer, a PCIe switch and an Ethernet switch. Each of the 8 nodes can be either or a CPU, a GPU, an FPGA, or an NVMe storage node. So basically, the customer can mix and match any of those nodes in an 8-block unit. And the 8-block units then again can be combined in a 24 unit that goes into a 3U that can go into a 3U chassis. So that means that the end user, and for the end user use case, we can create a fully customizable typology of a microdata center. We can make them storage centric, we can make them CPU centric, we can make them GPU centric, we can make them FPGA centric, depending on what the use case looks like or what the majority of the workloads look like. And of course, anything in between. And when you look then at a number of microdata centers, you can actually place some of those emphasis on the infrastructure itself, on the edge infrastructure. You look a little bit at the numbers here, the amount of cores that you can create. I think it's quite unprecedented what we're gathering here in a 3U chassis. A little bit about, So a little bit about how modular is everything and how can we scale. So the smallest units we're going to build is kind of a mobile enclosure. You could place it in a car, in a truck, mounted on a wall or on a machine, even on a small cell antenna, a 5G antenna. A slightly larger mobile enclosure is 3 times the 8 unit, 3 times the 8 server unit in a 19-inch half-depth 3U. You can still also mount it on a wall or on a machine or on a 5G antenna. The next level, of course, is multiples of the 3U units, which you would need to mount in a rack and then place in a small container on premise. A little bit about the cooling. So the cooling is almost completely solid state, which means we have, if you look at we have a monoblock through which we run a refrigerant, what do you call it, a refrigerant that is environmental friendly. The refrigerant runs through the monoblock, and we place the servers, we place them in the monoblock, which means that the cooling infrastructure is basically separate from the servers. They're not screwed together or anything else. We place the servers in the monoblock and then press them onto the cooling infrastructure. So we can design the cooling infrastructure quite rugged. Here at the bottom right, you see, oops, let's go back. Well, no. Here at the bottom right, you see the 3x8 unit monoblocks together. The refrigerant runs through the system based on flow boiling. So it's the system keeps itself intact. There's no pump needed. We don't need any fans within the server or within the microdata center. The only fan we might need is for the dry cooler to which the microdata center is connected. And that all depends on how big do we design the dry cooler, how big does the client allows us to design the dry cooler, what are the environmental conditions for the dry cooler. So that is something we can adjust for. The efficiency of the cooling system, we expect to be able to capture 97% of the server heat, which is, I think, quite extraordinary. And since it's almost fully passive, we can save 30% of the energy cost in the TCO. The heat can also, instead of sending it to a dry cooler, be also used to reused as facility heating. And I think an interesting aspect that also was already proven by IBM is that fluid cooling or solid state cooling has the effect of 10 times lower failure rates on hardware compared to air-cooled systems. So this is kind of a high-level view of what we're trying to do, and I hand over now to János to look a little bit deeper into the architecture.
Hello, everyone. So thank you very much for the quick introduction. I will do the deep dive now, and I'm sharing my screen. Hold on for a minute. Yeah. Is it okay now? Can you see it?
Yes.
Okay, good. So I'm János Lazányi, the CEO of PCB Design, and we are involved in this project, in this BRAINE project, to develop the EMDC, actually, the electrical part of the EMDC. And I have a general slide about us, because let's say we are not as big as Dell yet, so we have to maybe introduce ourselves in one sentence. We are a professional engineering center located in Budapest, in Hungary, and our primary focus is high-speed digital PCB design. And apart from this EMDC hardware, we are usually designing like explosion-proof tablets, rugged Ethernet switches, or quantum computers. So we release more than 100 PCBs. That's the measure we use each year, and we have a lot of interesting and successful projects. So if we go into the EMDC, you know, once Fred approached us, he wanted us to design this EMDC. First, we had to a little bit analyze what is on the market, and I would like to present this to you and to present the logic behind how we constructed together with all consortium partners this new EMDC hardware. So actually, of course, everybody does. So there's a call from someone, guys, let's design an edge data microsensor of data center. What you do, you go for Wikipedia and look what is an Edge MicroDataCenter. So I copied the phrase from there, and actually there are a lot of interesting things which we keep continuous in our brain just during the design phase. So it's a modular data center, and it's really important that it's not requiring traditional facilities. So as Fred put in this introduction, we were heavily thinking together with all other consortium partners to have it really mobile, to integrate the cooling system as well, and try to as flexible as possible. And also, it's important that it's not a single computing architecture or single computing node, but it's also including the storage, the switching, the power, and the cooling. So in this way, we can create a really scalable device with a quite reduced cost, and that's our primary target during the design phase. So I put in 3 slides the 3 main, let's say, competitors that we were analyzing a little bit. So the first one, and I think one of the most closest one, is this M2DC, which is a modular microdata center. And actually it's a Horizon 2020 financed project, and they are creating a 3U system with 9 carrier blades, and each carrier blade can be either 3 COMEXPRESS CPU type CPUs or 16 NVIDIA Jetson. And of course, they can use external accelerators with a standard PCIe device, so FPGA can be integrated into this system. So what is the takeaway from their system? I think is the most important, that for easy design, I think, and also for really easy adaptation and to prepare for new CPU types, they have selected as industry standard form factor, which is the COMEXPRESS, and the Type 7 is really focusing on server platforms. So actually, we also took this approach during the design, that the CPU node is an industrial standard. We are not designing it from scratch, but actually there are quite a few partners all over the world who are developing these COMEXPRESS modules, so we can easily integrate it as it's a standardized interface. So it's quite well future-proof as well. Also, we have like a universal architecture where a GPU can be integrated as well. Of course, NVIDIA Jetson is a little bit ruling out now, so but still we keep NVIDIA, and we use the Xavier AGX in the first system. FPGA acceleration is really important nowadays, and therefore we have used not the standard like Edge card, PCIe accelerator card, but we design a custom PCB to integrate to this small EMDC chassis. Also, networking speed is really important, and we have learned from the use cases that there is an enormous internal and external bandwidth requirement. So we put an effort on that to integrate much higher bandwidth on these devices, in this novel device. The other architecture that Fred already mentioned is this IBM Dome research project. Actually, I think the most important part here is that they are using a standard DIMM form factor, but custom PCBs, but also they introduced in this project this liquid cooling. So in this way, they could reach a really dense computing architecture. Unfortunately, this project, I think at the moment has no continuation. So it was just a development and research project, but actually it's interesting to analyze their results and see their architecture. And for example, what is the takeaway from here as well, that they use a central management node for, like, if I remember correctly, every 16 node has only one central manager node, which is actually saving on cost and power as well. And the last one that I put as a competitor is this Bamboo Systems. As you can see, they are also using this COMEXPRESS type form factor. And what is important, I think, that, you know, they are scaling up as well. So they have in one blade 4 COMEXPRESS modules, and they have 1 or 2 blades per 1U system. What is interesting, that as everybody on the world, they are investigating the ARM core instead of the standard x86 architecture. So they are using an NXP 2160 CPU for its main computing and processing node. But it's a COMEXPRESS module as well. So I think it's quite easy to adapt. So the takeaway from this is actually, I think that ARM node must be integrated in the system. So based on this, like, pre-seed research, we have created an architecture that is really universal, as Fred put, and based on the requirements, we can Lego together a system that is the most close to the application need. So what are the key hardware novelties in this EMDC system? EMDC, once again, is Edge MicroDataCenter. So this is the slide. I think it's a really high level slide that what are the key hardware novelties that we are designing is EMDC. As you see, no pictures yet, so it's only 3D rendering. The project has started like 9 months ago, so the first prototypes will come out actually in the following months. We were trying to prepare for a HiPEAC conference with real demonstration of cards, but as it's online, there was not a big pressure on us to get everything done by end of January. So what are the hardware novelties actually? So we have really heterogeneous node types. That's one of the most important. And all of the nodes, as Fred was mentioning, are having the same system connector interface. So based on the requirement, you can put together a system which is closest to your wish. What kind of nodes we are preparing in EMDC? So we have a standard Intel and AMD processing node with the Xeon processor and the EPIC processor. We have an ARM CPU node, which will be the EMAG processor for from Ampere Computing. It's a 32-core compute-intense card or node. There will be an FPGA node, which is the Xilinx Vercel, especially optimized for AI processing. And we have been using the GPU for, or the NVIDIA Xavier AGX GPU node and a small carrier PCB for that. Again, here we keep the modular concept. So whenever a new GPU will arrive to the market, we can easily adapt and integrate to our system because the system interface is really universal. And apart from this, if there is a requirement, there is a specific card, which is an NVMe storage, which is accommodating 8 terabytes of storage. And based on these cards, you see on the top picture, a 24-slot system in a 3U chassis. You can really Lego together whatever you want. If you need only processing, you can put Intel or ARM cores. If you need more storage, then you put some storage nodes. And based on this, it's a dynamic configuration of the system. It's really fine granular architecture. So the smallest system that we can Lego together is an 8-slot system, but it can build a 16, 24, 32 nodes in a half depth 3U chassis. So if required, even more can fit in a 3U to the back, let's say in this way. What others are there? So actually, I want to underline this 2-layer of switching. So actually, there is a standard network switching for each and every card. Each card gets a 100G interface. So I think it's quite interesting because there is a really big bandwidth for each and every card, and it's again for future-proof as well. And on the back side or on the front side, we have 8 times 100G interface for connecting it to the external world. And there is a 6.2 terabit per second aggregated switch, which is also one card in the system. It has, of course, a dedicated slot, but it's also one module in the system. The other switching is actually PCIe switching. Fabric switching is just recently introduced to the market. There's a Gen 4 PCI Express fabric switch architecture in there. So actually, the cards can talk to each other with a ultra low latency. So no Ethernet communication is absolutely required. And also this fabric switch is used to connect the NVMe storage to the appropriate CPU node. And it can be, of course, dynamically allocated as well. About the power, we are using a 48-volt input power rail because we will see the power dissipation of these racks are immersed. So we had to go for 48-volt. And what Fred was mentioning, there's really an innovative 2-phase cooling. So each and every card in the system is designed to have maximum 150 watts power dissipation. And we can cool this in this fancy way from this 3U chassis and connect to an external condenser. So if we go into a bit more in details, this is really the high level thing. This is the first thing we put on the whiteboard. So actually there are 8 nodes and each node has an Ethernet switching and a PCIe switching capabilities. And apart from this, the smallest system has a chassis management. So this is the super simple architecture that we put on the first day together with all the consortium partners. And if we deep dive into a little more in detail, what Fred was mentioning, we can put only CPUs in the system. So it's a cluster of computers. We can build an AI accelerator with the GPUs in the system or FPGAs, and maybe only one centralized CPU. Or if a really storage requirement, we can put in all of the nodes, like storage nodes in this way, and an external network interface card. So it's really a like a storage area network or something like this architecture. What is also important to mention, and Peter will deep dive into this after my introduction, that both the GPU and the FPGA is a system on a chip. So it's not a slave device, or it's not a target on a PCIe bus, but it's really an independent node. Each of the GPUs and FPGA will run its own Docker image. It will have a Kubernetes entity. So actually it's not a simple slave device, but actually it's also acting as a CPU node with some acceleration capabilities. If we talk about the node types, so I will have a short introduction about the nodes. So these are the nodes that you can plug and play into the chassis. On the bottom picture, you see a equipped 24-slot system. And for example, I put one of the CPU modules that we are investigating to be used in this EMDC system. So it's a Congatec ComExpress Type 7 CPU. It's an AMD EPYC processor with 16 cores, maximum 96 gigabytes of RAM, and onboard 2 terabytes of SSD. So you don't have to buy or configure NVMe storage nodes if you don't need absolutely. There are 2 terabytes of SSD available for each and every CPU node as well. So that's a good example. So how strong this system can be. And apart from this, as I mentioned, we have the EMAC 8180, a 32-core ARM processor. We have the NVIDIA Xavier AGX and the Xilinx Versor AI SoC. Apart from this, there is a NVMe storage build, and the smart NIC is also planned for future applications. And apart from these general nodes, there are 3 different cards, which are like system cards. One is the Ethernet switch, another one is the PCIe switch, and of course the board management controller, which is able to serve maximum 24 like worker nodes and all the rest of the system. So that's actually forming one big monolithic design. How the CPU node looks like, if you are interested in details. So actually it's using a ComExpress module, which is a 95 by 125 millimeters. And actually our module size is determined according this. So you see that only we extend 21 millimeter on the height and 14 millimeter on the width. And actually there is a small carrier board carrying the ComExpress module, and of course some other components like BMC and flash storage and some Ethernet controllers. But actually it's an easy concept, let's say, in this way, that there's a lightweight carrier board which is holding the ComExpress module, and of course integrating to the system interfaces of the EMDC. On the right side, you see wedge lock system. So it's really important. Don't forget, we have 150 watts per card to take away or to dissipate to the block, to the mono block. So it's not using the wedge locks to transfer the heat. So the full light blue area is used to transfer the heat from the CPU towards the bridge of the mono block inside the EMDC system. We are using a novel, let's say, a sliver connector from TE, which is able to handle maximum 56 gigabits per second. It's a PCIe Gen 5 compliant and all this kind of thing. So actually, it's quite future-proof because we are really taking into account the flexibility and the future-proofness. What is important, we have a dual power rail system in the card defined. So actually, you will see that the ComExpress module by native, they are using 12-volt system. So we are feeding them 12 volts, not to have any other power conversion loss. But for those cards who are really high power, we are using the 48-volt directly. So in this way, it's you can optimize the power of the system. And maybe we can think that 12-volt is like a legacy, but still it's a ComExpress module and ComExpress standard. This is the one that defines. So anyhow, we need to convert somewhere the 48 to 12 volts. So in this way, we have a centralized power node you will see later, which is doing this quite efficiently. Well, returning back to the CPU node, what are the features we are presenting here? So actually, there is the ComExpress CPU in the center. There is the BRAINE slot connector on the bottom, and as you see, there is a 1G management interface. There are up to maximum 4 10 gigabit KeyR interface. Actually, it could be 25 as well, but this ComExpress supports only 10 gigabit by this time. We have 2x8 PCIe fabric links. And we have the KVM interface for the central BMC. So actually you can access the BIOS of the ComExpress remotely. You can have the monitor attached to this single node and mouse and keyboard. So you can remotely manage each and every node separately. On the right side, you see our proprietary BMC subsystem. It's working over actually USB, and this is the one which is identifying the card that being inserted in the system. And based on this is configuring the PCIe switch and the network switching and all this kind of things. It's important that you see on the block diagram 2 TPM chips, so trusted platform modules. So actually both the BMC has the TPM chip and both the ComExpress CPU module, because security is super important. So actually both communication towards the central BMC and of course the ComExpress module itself has its own hardware cryptography features enabled. And there are 2 storage on the ComExpress module apart from the ComExpress module. One is a BGA SSD, so it's a maximum 512 gigabytes for operating system, and there's an M.2 SSD for 2 terabytes of external storage. And actually that's how the ComExpress module carrier is built. As you see, it's rather simple. And you can have a lot of different CPU types combined together with carrier boards. So for example, the AMD EPYC processor, as I mentioned, or Intel Xeon. There is this ARM processor, the LX2160, which is a 16-core A72 processor. Or, for example, there is a HiSilicon with a 32-core. So actually, there are quite a few on the market, and you can mix and match, and based on your based on your cost margins and based on performance requirements, you can build a system with the same carrier with all different CPU types as well. I think I mentioned the storage, networking, fabric switching. So actually, this is the heart of the EMDC system. It's a small carrier board and the standard ComExpress module. If we go for some other modules, so for example, you see here, I don't know how to hide this, but hope it's okay. So this is the ARM CPU node. This is with eMAG 8180 processor. It's really for performance optimization, and it includes a 32-core ARM architecture 8, and it has an onboard 100G Ethernet interface. Sorry, 50G Ethernet interface. It's 2x25 or 10G. It has also the TPM chip, the BGA SSD, and the board management controller. So the architecture looks quite similar, but it's in this case a dedicated PC with this Ampere processor. You will see it's a bit blurred now. So the FPGA and the GPU nodes, I don't want to go into details. Peter will talk after my presentation in details about those other 2 nodes. So actually, this is how the EMDC system is built. So let's talk about the auxiliary peripherals and auxiliary components a little bit. So how the construction looks like. So we call it monoblocks. This is a monolithic block. Actually, it's a proprietary way to manufacture. So this is capable to handle for each and every slot 150 watts once again. And between the slots, there is a brick. That's how we call a cooling bridge. And actually, each and every module is dissipating heat to that cooling bridge. And there is this special liquid cooling system in there, which is taking away the heat. So in a monoblock, there are 8 processing nodes, and there is one power node at the end. So you will see later on, which is converting the 48 volt to 12 volt. And we have the PCIe fabric switching, which is also optional. So it's really customized architecture. So for example, if you don't want to use the fabric switching or PCIe fabric switching, you just omit the card, you save cost. And and you use the Ethernet for switching. Then there are some special slots, which is the last one in each and every monoblock, which can be either a BMC, so the board management controller, it can be an Ethernet switch, or the hierarchical PCIe switch. You will see a block diagram a bit later. About the cooling, so I think that's one of the most interesting part. We have a partner in the consortium called GG Cooling, and they are the experts on this, but I try to give you a quick overview on this. So it's a two-phase gravity driven cooling system, and it's a thermosiphon, and between the cards we have only a 6 millimeter thick cooling bridge, and this is able to carry away the 150 watts per node maximum, and the cooling performance is such good that from the temperature or from the big brick or from the wall in between towards the CPU, it's only rising around 5 to 6 centi Celsius. So actually we don't need to use any special components. Standard CPUs can be used, and the rough temperature that we are targeting at the moment is absolute maximum ambient 40 centigrades. So if we put together this 150 watts per node, it turns out that in a 24 slot system, we will have to dissipate like 4 kilowatts, and in a 42U system rack, so it will be 56 kilowatts. And don't forget, once again, it's no fans, no moving components, nothing there, just a special construction, gravity driven. And in the next slide, you see how it works a little bit. So I'm not an expert in this either, but actually on the brick walls, you will see these super micro tiny channels where there is this special liquid is flowing, and it's evaporating actually when the heat is applied. So when the CPU module, for example, is touching that wall, and from the liquid phase it's going to vapor phase, and from the pipes through the pipes it's connected to the extender condenser, and this condenser is built like this. So there are super micro channels. These are standard condensers, so you can buy it in a shop, let's say, in this way. And then after this condensation, it's decreasing its temperature, some, not much, 1, 2, 3, 4 centigrades, and going back to liquid phase again. And this is actually a gravity driven cycle. The only, as Fred mentioned, the only part where we might need external fans is actually at the condenser. So if the amount of heat you need to take away is exceeding the surface here, so external fans might be required on the surface of the condenser to take away the heat. But again, it's not in the server room, it's not in the same room, it can be somewhere else, and outside or inside. And based on the heat requirements, of course, different condenser sizes are required, but these, just think of them, these are tiny small devices, and inside the server rack, no moving parts again. How the system looks like. So this is on the left side, you see a 3D print capture from our system, or from the hardware design system. So you see the 3 monoblocks on top of each other. The last one is removed. You see ComExpress cards here, 8 of them. At the last one, there is this special power node, which all 3 is populated in this case. In the middle, or you see the processing nodes. So actually it's again FPGA, GPU, CPU, or ARM CPU. And on the left side, you see some differences for each and every row. So actually the blue cards here are the PCIe switches. There are 4 in the system, 3 for each and every row, and there is a hierarchical PCIe switch. And apart from this, on the first and the last row, you see the board management controller, and you see the Ethernet switch card, which is also eating up a single slot in the system. And on the front, you see 8x100G Ethernet interface, QSFP28 socket. So actually, this is really the general overview. Hope you got the idea behind. And if you go a bit more in detail about the BMC, so the board management controller, we use a really industry proven and standard AST 2500 controller, which is able to serve us to identify each and every node during boot, to get their memory configuration, and apart from this, of course, this will be the one remote monitoring each and every node, like temperature and power. It has a serial console over LAN. It's able to upgrade the remote BIOS for each and every card, and it has watchdog features. And so yeah, so the centralized BMC are providing this feature at high level, and like also keyboard, video, mouse over Ethernet or real connection. So all these kind of standard features are available, and also we are planning to use the OpenBMC platform for this with the Redfish support. And on each and every node, there's a small microcontroller which is talking over USB to the centralized BMC. And these are the ones that actually executing all these features that is requested. And these node supervisor BMCs, they are residing in each and every card. They are standardized. So it's really easy to implement any other new node types based on this architecture. We didn't want to use actually Ethernet interface for management because we need to add one more Ethernet switch, and it gives more complexity. So actually, to save power, to save complexity, we are doing the remote management over USB, and this is quite fine working as well. About the Ethernet switch. So the Ethernet switch, now you see on the bottom a picture from the bottom view of the EMDC nodes. It's a Mellanox Spectrum switch. Mellanox is also a consortium partner. They are providing the Ethernet switching part. It's one slot in the system, so don't forget, again, it's like 120 by 160 millimeters. So we squeeze it in 3.2 terabits Ethernet switch to this small space with one of the best connectors on the world. And actually, this is serving like 24 worker nodes. For each and every worker node, you will get once again 100G connection, and there are 8 times 100G external connection. We are hardware guys. We don't do that much software, but we know that the ONOS controller will be used at high level from Kubernetes interface. This will be able to be reconfigured based on the requirements. So actually, no external top of rack switch or nothing is required. It's integrated in the system. It's one of the cards there. And again, if you might not need Ethernet switching, just don't populate the card and it's there. But most probably in all the cases, you will need Ethernet switching. About the PCIe switching, so actually, as I always mention, it's a hierarchical PCIe fabric switching, whatever it means. So it means that for each and every 8 node, we have one PCIe switch. They are closely coupled. So actually, we say that each and every module can be plugged anywhere, but there is, of course, some kind of, you have to have some awareness of the hardware configuration. So those slots which are residing in an 8 block, they are, let's say, closer from PCIe look point of view. So if you populate, let's say, the first 4 with CPU, the others 4 with NVMe storage, then it's an optimal configuration. So of course, this is a closer proximity. And apart from these 3 of these monoblocks, or 3 of these 8 times nodes are coupled together with a PCIe hierarchical switch. If you might remember, there was a separate slot for this. Actually, the switch cards are, again, they look the same, they are the same. So actually, if you don't need this hierarchical switching, you just don't populate that card. You can build your own hardware configuration as you wish. What is the PCIe switch? So actually, we are capable to use both Broadcom and Microchip Gen 4 PCIe switches. At the moment, we start with a Microchip solution. There is a big movement on the market to get this fabric switching up and running. So there is a big software development in the background. At the moment, why is it good actually? So actually it's good because each and every host can have of course, it's hypervisor and virtual machines running, and also on the slave devices or on the target devices, we are supporting SRIOV, so IO virtualization. So as on the picture, you see each and every host virtual machine can connect to any slave device virtual function. So it's really a nice mesh, and you can build whatever you want. So that's, let's say, the hope, that's the wish. At the moment, the switch firmware doesn't support this always fully. So it's there. We are prepared for that. At the moment, the first release is, of course, we will use more like a standardized PCIe switching. But don't forget, there is a nice 2x8 lane towards the switch possibility. So there is a significant amount of bandwidth towards the switching, and it's now Gen 4 option. So last comment on the power. So we have in the chassis 3 power nodes, and each power node is consuming, or it's built up from 4 really high efficient 48 to 12 volt converters. So each power node is able to carry 3 kilowatts of power, and with a 97% peak efficiency. So in this way, in the system, as I mentioned, we have a 48 volt bus for really the high performance module. So it's a direct connection to the 48 volt bus for the FPGA, the Xilinx Versal, or the ARM EMAG processor. And for the rest of the modules like PCIe switching or the ComExpress modules, they are able to use the 12 volt bus subsystem. So in this way, each and every module can decide if it's using a more efficient 48 volt direct input or it's a 12 volt intermediate voltage. It's more or less to support the legacy systems. We were first targeting for 48 volts only, but we realized that the market is not that much ready. The components are not ready to have such a small integrated low footprint solution for like point of load regulators for auxiliary voltages. So in this way, we kept the 48 and the 12 volt, but the 48 is definitely the future, especially if we think about such a big power consumption. And actually, this is the last slide for me. And I would like to dedicate this presentation to my former boss, Bela Feher, who is actually the local organization chair for HiPEAC conference. And he actually, unfortunately, died in COVID. So with this last picture, I really want to say thank you for him. And I would like to give now the presentation for Peter, who will be the next one in the chain. And thank you very much. And if you have any questions, feel free to ask. And at the end of this session at 12:30, I am happy to answer any upcoming questions. Thank you very much. Peter.
Thank you for the presentation, Fred and János. And please stop. Okay, thank you. Okay, can you see my screen correctly?
Yes.
Okay, thanks. So as János mentioned, I will talk about the heterogeneous accelerators inside the EMDC. My name is Peter Santo. I am from Budapest University of Technology and Economics. Actually, our main responsibility in the BRAINE project is the FPGA node, was the internal design of the FPGA and the software part of the FPGA. But I will also discuss the GPU node. First of all, the architecture decision. As János and Fred mentioned, we decided not to use the traditional host and accelerator separation. So we don't have PCI Express based accelerator nodes. Instead, we decided to use system on chip devices which are capable of operating as standalone nodes and still offer some kind of acceleration. The main reasons behind this decision was that, first of all, edge servers are not HPC servers. So the number of workloads are larger, and while at the same time, the workloads itself are typically smaller. So we need fine-grained workload distribution, which seems to be easier if we have several smaller nodes. Then another thing which is not present in HPC servers is latency. For some of the use cases, latency could be a critical issue, and in this case, smaller so-called embedded system may offer better performance than large-scale devices. The second thing is modularity. As it was already mentioned, we want to let the user mix and match different types of nodes. And if we don't require the accelerator nodes to have another specific node to be able to operate, then this mix and match could be much easier. And finally, and most importantly, the aim for the highest possible efficiency and not for the highest possible performance. So what we want to optimize is performance per watt. And now move on to the nodes itself, starting with the GPU node. As János mentioned, our GPU node is based on NVIDIA Xavier SoC. And this SoC, as we will see, contains not only a GPU, but a lot of other stuff inside, including a CPU core complex. NVIDIA sells this SoC as a system on module, which you can see on the bottom right of the slide. In BRAINE, PCB design will design a PCB, which is a carrier board for this system on module. The schematic of this carrier board looks quite similar to the CPU boards. It integrates a power subsystem, the board management microcontroller with the TPM chip, the BRAINE connectors with PCI Express fabric, and 2x25G Ethernet. Beyond that, we will have the usual debug connector with USB and Ethernet, and next to it, we will have special interfaces for the GPU node, which is an HDMI output and several MIPI CSI2 inputs to be able to connect cameras directly to the GPU node. Other than that, we will have an on-node storage, so it won't have to always use the NVMe node inside the EMDC. So as you see, it's pretty typical in the sense of EMDC node. Inside the Xavier, we find an 8-core CPU, which is based on the ARM instruction set. These are NVIDIA's custom designed Carmel cores. The frequency is not that high, it's only 2.2 gigahertz, but this is a 64-bit ARM core with relatively large caches and a lot of instruction set support. Obviously, it supports floating point instruction, 16-bit floating point, cryptography extension, and single instruction multiple data instruction set. Next to the 8-core CPU core complex, we have a GPU, which is based on NVIDIA Volta architecture. We will have one more slide about this. And what is really special for the Xavier, it's the NVIDIA Deep Learning Accelerator, which is actually an open source core from NVIDIA, and they implemented it inside the Xavier. And next to them, we have a multimedia complex, which contains video encoders and decoders, JPEG encoder, decoder, and some other hardware modules for video and image processing. And the highest power mode of the Xavier is a 30-watt power mode, when it can run all the CPUs and the GPU together. Moving on to the GPU, as I mentioned, it's an NVIDIA Volta generation GPU. It has exactly the same internal architecture as the Volta-based server GPU from NVIDIA, namely the V100. Inside the GPU, we have 8 streaming multiprocessors, each having 64 CUDA cores. These CUDA cores can work on floating point, 16-bit floating point, and integer operands. Next to the CUDA cores, we have tensor cores, which are capable of accelerating matrix multiply and accumulate operations using 8-bit integer operands or 16-bit floating point operands. And these tensor cores are aimed to accelerate AI inference or AI training. And altogether, in the 8 streaming multiprocessor, they offer 22 teraops if integer operations are used. The NVIDIA Deep Learning Accelerator has more or less similar architecture as the tensor cores. They also accelerate the matrix multiplication using the exact same type of operands, so 8-bit integer and 16-bit floating point. We have 2 DLE accelerators within the Xavier, and they offer 10 teraops when integer operands are used and 5 teraops with floating point operands. The good news is that this GPU is completely the same, even from the software point of view, as the server GPUs. It just has a little bit smaller number of streaming multiprocessor, therefore lower performance, but the capabilities and the development is absolutely the same. Beyond the GPU and the DLA, there are other dedicated hardware engines. The first one is the video image compositor. It allows the Xavier to accelerate video and image processing in hardware. Namely, it can do video and image scaling, color space conversion, and noise reduction. And actually, the hardware itself supports pre-geometry transformation, but at the moment, this is not absolutely supported from the hardware APIs. In several applications, video decoding and encoding is also an important feature. For example, in telco business, when video transcoding is used, and the Xavier is really, really capable in this respect. The video decoder supports all formats which can be, which is used nowadays, and they can decode 6 4K videos at the same time. The video encoder, on the other hand, supports only 3 formats, and the performance is a little bit lower. It supports 4 times 4K video stream encoding. Still, this encoding performance is much larger or higher than any of the other encoding chips on the market. It's even higher than NVIDIA discrete GPUs. And finally, we have NVGPEG, which is a JPEG decoder and encoder for still image processing. On the software side, we have Linux for Tegra. This is the operating system of the Xavier. With the Linux for Tegra, we have several APIs for accessing different hardware accelerators, namely for multimedia video processing. We can use GStreamer, which is an open source API, and we can also use NVIDIA's own multimedia API. For 3D graphics acceleration, we have OpenGL and Vulkan support. And finally, for general purpose GPU acceleration, we have CUDA 10. And as I mentioned, this is the same CUDA which is used on the desktop or other server GPUs. And the other good news from the point of BRAINE is that the Xavier supports NVIDIA EGX2 platform, which has an NVIDIA Docker runtime integrated, and this NVIDIA Docker runtime supports GPU hardware acceleration out of the box, and which is even better, it also has Kubernetes support. So this node should be able to integrate it into the EMDC out of the box. Now let's see some proof of the concept of using standalone GPU nodes instead of having PCI Express-based accelerators. This is an AI inference benchmark in offline mode, which means that all of the workload is submitted to the GPU at once. This means that even the highest parallel architecture can offer the highest possible performance in this mode. And as you can see, the NVIDIA Xavier is much slower in absolute performance than NVIDIA's server GPU, be it on NVIDIA T4 or an NVIDIA A100, which is the highest performance NVIDIA GPU for servers at the moment, is based on the Ampere architecture. So in this case, the Xavier can only achieve 10% performance of the A100. However, if you take into consideration the power consumption, this A100 is a 400 watt GPU, while the Xavier has 30 watt of power consumption. So if we measure performance per watt, then we see that Xavier is on top. So if we don't aim for the highest possible performance, but the highest efficiency, Xavier is the better choice. If we run a benchmark which is latency critical, this is the single mode of the MLPerf benchmark suite, which only send one workload at the moment and send the next one if the GPU is finished with the previous one. In this case, the absolute performance of the NVIDIA Xavier is higher. It achieves 10% of the A100. The power consumption is more or less the same, so the relative efficiency of the Xavier is even higher than in the previous case. It's 3 times as efficient as the NVIDIA A100. So for low power edge server architectures, the Xavier is a better candidate than the high-end server product. This slide is an interesting one. Although we don't actually plan to use the Xavier as a TPU node, it makes sense to measure performance and efficiency without using the GPU. These numbers are from Phoronix benchmark suite. They are some compression, graphics processing, video and audio encoding, raw mass function, and software compilation function. As we can see, the absolute performance of the AGX Xavier is much lower than higher-end CPUs. Here you can see the Ampere, which is a 32-core ARM processor, the AMD Ryzen 7, which is again an 8-core x86 CPU with 64 watt TDP, and one of the Intel Xeons, again an 8-core CPU with 85 watt TDP. So these 3 CPUs has much higher performance than the 8-core Xavier. But again, if we check efficiency, Xavier comes first almost in every case, except the software build. Only the AMD Ryzen can compete with the Xavier. And for the future, an interesting notification is that the 32-core Ampere CPU with its relatively high TDP doesn't seem to be that efficient at all. So maybe we have to re-benchmark it or think a bit about if we want to really use it or not. Okay, moving on to the FPGA node. Our requirements about the FPGA are it has to be able to operate as a standalone node, so it has to contain a CPU core complex. Such a SoC FPGAs are available from Xilinx or Intel and even from Microchip. The other requirement is that AI performance is a priority for the EMDC. And at the moment, it seems that AI performance, the best AI performance is offered by the Xilinx Versal AI FPGAs because they integrate a dedicated hardware block for accelerating AI inference. The peak performance of the Versal chip we want to use is 108-bit teraops, which is 3 times as fast as the NVIDIA Xavier. And beyond this AI accelerating core, the Versal has a lot of FPGA resources, a lot of high-speed integrated memory on chip. If you take a look at the schematic of the FPGA node, again, it's look more or less the same as the other nodes. We have the power subsystem, the board management, the same BRAINE slot connector as in the other modules, 1 time PCI Express fabric and 2 times 25G Ethernet fabric. We have an onboard on-node SSD for local storage, and we have 4-channel DDR4 memory. The difference is that this is a custom PCB designed by PCB Design, and it is a one-chip solution. So every interface is inside the FPGA itself. As the Versal is a little bit special, let's take a look at the internals of the chip. One of the parts we will use is the processing system, which contains ARM 4 CPUs. The other one is the programmable logic part, which is the general FPGA logic, which you can find in other Xilinx FPGAs. And other than that, we have the so-called AI engine array, which is the programmable hardware component to accelerate AI inference, or actually other DSP stuff. Then we have dedicated 100G Ethernet connection, which can be used as 1 time 100G or 2 times 50G or 4 times 25G. And we have 4 DDR4 memory controllers. All of these hardware parts are connected together with a network on chip infrastructure, which is a really high-speed AXI-based connection infrastructure. Okay. The interface blocks which will be used on the FPGA node are the 4 memory controllers, which support 64-bit wide memory interfaces. We will use 2 PCI Express blocks, one for communicating with the other nodes and one to communicate with the onboard SSD. And we will use the multi-rate Ethernet MAC, which will provide us with the necessary Ethernet connection to the BRAINE connector. Let's take a look at the other hardware parts. The application processing unit contains 2 ARM cores, which is actually ARM-designed A72 CPU cores. So we don't expect to have so high performance CPUs as in the Xavier or in the CPU nodes. Still, it's a 64-bit ARM architecture supporting out-of-order execution. It also supports floating point cryptography and vector instruction sets, and it also supports virtualization, which is a good thing when we want to run Docker images. The other part of the processor system is a real-time processing unit, which contains low-performance Cortex-R cores. We don't plan to use them for the BRAINE. And other than that, we have quite a few peripherals, either for the outer world or to connect the FPGA and the AI engine part of the system with the processor system. The most interesting thing in the Versal is the AI engine array. It contains 24 AI engine ties. These are the actual processing ties. These AI engine ties can communicate with other parts of the chip through its interface ties. We have 2 types of interfaces. One for the programmable logic. This contains an AXI4 stream interface for FIFO-like access and the memory mapped AXI4 interface for memory accesses. And we also have an interface for the network on chip, which features everything the PL interface does. And beyond that, it also has an integrated DMA controller, so it can act as a bus master. And finally, we have a slave configuration interface, which can be connected to the network on chip so that the CPU cores can configure the AI engine array. Within the AI engine array, we also have several communication possibilities. The neighboring AI engines can communicate through their internal memories, and non-neighboring engines can also use these memory and the integrated DMA engine to communicate with each other. These are all memory-mapped communication interfaces, so they are addressable. And other than that, we have an AXI4 stream interconnect between the AI engines, So it is also possible to do FIFO-based communication between the engines. The engines itself are very wide vector unit with VLIW instruction set. In each instruction, we have two operators for the scalar CPU, two load operators, one vector operator, and one store operation. The vector unit itself contains of a floating point unit and a fixed point unit. The fixed point unit is, and actually both units are 512-bit wide. When using the floating point unit, the only option is to use 32-bit floating point data. When using the fixed point unit, you can have 8, 16, and 32-bit operands. And in the 8-bit case, one of these AI engines can do 128 multiply and accumulation operation in one clock cycle. And because of the instruction set, together with this multiply and accumulate, it can also execute an instruction on the scalar unit, and it can also load and store data from the memory or write data to the memory. The address generator of the load unit contains flexible addressing mode like fixed addressing, cyclic addressing, and addressing for FFT. And beyond these computational units, we have a relatively large memory, which is a 32 kilobyte integrated memory separated into 8 banks, and these 8 banks can be accessed in parallel. If you take a look at the how to program the AI engine, it's more or less similar to GPU programming, but it isn't absolutely the same. Here we also have a kernel, which is the code of the AI engine. Kernel code is written in C++, but the input-output is different from the traditional GPU kernel. We have two options: a Windows-based input-output, when you can provide data in an array to the AI engine, or we can have a stream-based input-output when you provide a FIFO interface to the AI engine. One drawback of the programming of the kernel is that there is no automatic vectorization. So unlike CPU programming, you have to use intrinsic instructions to be able to take advantage of the vector processing. And after you have written the kernel code, you build a data flow graph using only one kind of kernel or several types of kernels. And you can connect these kernels together by connecting the inputs and outputs of the kernel. So unlike a typical GPU processing on the AI engine, you can run several different kernels at the same time. And finally, we have a custom API for the host code, which is running on the ARM CPU cores. This is called the Cardano API. It's really a custom API for the AI engine. Behind the AI engine, we have the programmable logic, which is the usual FPGA logic. It's based on configurable logic block, just as it was on previous Xilinx FPGA generations. It's still based on 6 input lookup tables. Half of them can be operated as small internal memories or shift registers. There are some simplifications in the architecture, like simplified carry logic or the removal of wide multiplexers, but we expect that these simplifications won't affect performance too much. Which is brand new in the PL part is the MAC unit. It has wider input than in previous FPGA generations. It also supports floating point operations on 32 or 16-bit floating point numbers, and it is also supporting 3-element dot product mode, so it can be efficiently used to accelerate AI inference if the AI engines are not fast enough. On the memory block side, these are on-chip memories within the programmable logic. Nothing has changed from the previous generation. We have smaller block RAM memories and larger ultra RAM memories. But the peak bandwidth of these memories are extremely large. In the chip we will use, it's something like 18 terabytes per second. On the development software side, you can use Vivado or Vitis, which is the traditional development for Xilinx FPGAs, but for server-like development flow, the Vitis accelerated development flow is the preferred way. This is an OpenCL-like development flow, where the OpenCL kernel itself is the kernel which is accelerated in the programmable logic, or it is accelerated inside the AI engines. And the host code, which provides data management and configuration functions, is the OpenCL host code. The kernel code can be written in OpenCL, and for the PL, it will be compiled by Vitis HLS, which is a C2 FPGA compiler tool. For the AI, it should be written in the AI engine custom development flow. And then you can integrate this kernel with the OpenCL host code and generate the accelerator itself. The OpenCL host functions uses the Xilinx runtime API to configure and communicate with the kernels. If we take a look at a higher level, then we have during the programmable logic and AI engine development, we have quite a few libraries Xilinx provides. For the programmable logic, we have almost all the OpenCV function, BLAS function, and compressor function, which are accelerated in the programmable logic out of the box. For the AI engine, at the moment, we have Vitis AI, which is capable of accelerating AI inference. And we should have Vitis Video soon, which will contain video processing function and video encoding and decoding accelerated on the AI engine. On the server level, the situation is not that good as it was with the Xavier, as there are no Kubernetes device plugins for the embedded FPGAs from Xilinx, only for the server products. So we have to write our own Kubernetes device plugin, which will report the FPGA resourcing and which will report performance metrics to the higher levels. And we also have to create our Docker runtime, which will be able to use the programmable logic and the AI engine acceleration within the FPGA. This Docker runtime, which we are working on, uses the Xilinx runtime library, just as the OpenCL development pro from Xilinx. These are in progress developments. So I would like to thank you for your attention. And I will stop screen sharing. And as far as I remember, now we will have a short break again. And afterwards, we will continue. Just 1 second. Okay. So I was a bit long. Still, we will continue at 12 o'clock with the second part of the software by Javad Shamanara. And now we will have a short coffee break. Okay, let's continue. Javad, I would like to ask you to.
Thank you, Peter. I'm sharing my screen. Hopefully you can see it.
Yes,
and I'm putting it on the presentation mode. Okay.
Okay, great.
Okay, so hello, everybody. I will continue with the software part. In this case, I will continue again with some of the components that we are building into the overall architecture to see how the BRAINE EMDC is working. So before that, if you remember from John's presentation, this is a modular EMDC here from the hardware perspective. Let's see how we can model it from the software perspective and then how to build on top of that. So first of all, the first thing that we build on top of this is a concept of software nodes. This software node is a full computer from our perspective. We will see more details about this so that the modules that Janus mentioned, like GPU modules, CPU modules, FPGAs, except the storage nodes, they will be actually the software nodes or software computers that we will put them together into a cluster. So this would be node 1, for example, this would be node 2, and so on and so on. And the whole EMDC here will be modeled as a cluster. There are some proposals under investigation in the consortium to have multi-cluster per EMDC, but the mainstream is going to have one cluster per EMDC. So let's see what other options will come in the future. So for simplicity, when we are talking about a cluster here, we're basically thinking about an EMDC node. So inside this EMDC node, we have this kind of computers. So let's say, for example, here, node 1 is working on 4 CPUs number 1 to 4. It has its own operating system on it, and then that operating system is controlling the resources, like if there is a GPU, if there is any storage, network, memory, and anything that is available to that operating system will be actually shared with the cluster for resource management later. And then as you see, the nodes are sharing nothing except their network. So if there is a PCI internal to the node, it will remain internal. But between the nodes here from software perspective, all the traffic will go through the network. So there is no, let's say, memory sharing here or no PCI bus between the nodes and so on. So then we divide the cluster into 2 types of node or software nodes. Most of them will be worker nodes that are actually doing or executing the workload. And 1 or more of them will be a manager node that is controlling the other nodes by assigning them the workload. So in order to make this happen, we are using a cluster based on Kubernetes from Google. And in that case, each of the worker nodes should have an agent that is called kubelet, that this kubelet basically communicates with the controller here to first announce the maximum and current resource availability, and second, to accept the workload from the manager node to bind it to one of the CPUs here or to multiple CPUs or any other resources that is requested by the workload. So from now on, when we are talking about a node, basically we are assuming this kind of like a complete hardware plus operating system plus the agent on top of it. And then on top of those agent or side by side with the agent, there is a virtualization platform that we are using Docker. And then the workload goes on top of the virtualization platform and will be executed there in a sandbox. So, but in order to make everything separated and also to have this kind of separation of responsibilities and characteristics between different components of the system, we have come up with this 5-layer software architecture that on top, on layer 5, you see the application layer, we have use cases, so that use cases will actually formulate their workload in terms of a workflow authoring tool that we are designing and building in layer 4. They have access to data management and monitoring information and so on to be able to explicitly and with some sort of assistance from the system to be able to specify their workload. And then when the workload is defined, that will be passed to layer 3, that is the infrastructure layer. Here, actual work placement happens, resources are collected, service information is collected, distributed file system is here, and also the telemetry framework is here. The pieces that Janus and Fred have explained are actually modeled here in layer 2 as hardware. So here we have a set of nodes that are communicating via a network, and they are managed by a management node or a set of management nodes. And then these nodes here are able to talk to each other and also talk to external systems. Let's say, for example, this is a single EMDC. This can talk to another EMDC via layer 1. It can talk to IoT systems or legacy systems or other cloud services outside of itself via the external facilities that are here in layer 1. So for today, I'm going to introduce some of these components here. Let's say, for example, work placement, telemetry, and 1 or 2 of the use cases, basically to show you what we are doing there and how machine learning and AI is integrated into the whole structure, not only at the application level, but also at the internals of the system. So here for the first component, I will go through the work placement characteristics and features and responsibility to see how it's going to work. So first of all is that work placement is a component that accepts a job from, let's say, a user or another machine and tries to find a proper node and ask for execution. So it will ship the workload to that node, and the node will run the workload that is assigned to it. So, but as a general scenario is that this user will define a workload by the authoring tool is like a visual textual assisted authoring tool that we are developing. Actually, some of our partners are developing that. So a user will come to this interface, access to the policies, to the resources, to availability of the resources, to SLA terms, and so on. And from all those constraints and definitions and so on, she will create a workload. And then that workload will be submitted to the manager, to the orchestrator of the manager, and it will be enqueued for execution here by the controller. After some sort of waiting here by pre-processing and so on, it will be shipped for scheduling. So this scheduling is the place that we will see in more detail. This is the component that decides which nodes should take this workload and execute it. When the decision is made, the controller will be aware of that, and then it will bind it to the selected node here. So these are the worker nodes, and then the rest of the system, I will go through it later one by one. So here you see that the nodes are actually those independent nodes with all their resources, but at the same time, we are building an overall distributed file system on top of their local file systems or on top of those storage nodes, so that if there is a workload that is moving between the system, between the nodes, it still can access the data that was, let's say, produced by another node or produced by another application on another node and so on. So in brief, is like that. We have a cluster that has a manager part that is possibly 1 or 2 nodes, and then the rest of nodes are worker nodes. When the workload is submitted to the controller, there should be a scheduling here that we call it L1 scheduling. L1 scheduler is responsible for scheduling and placing the work on one of the worker nodes. And then when the workload arrives, for example, here on node 7, there is also an L0 scheduling here that is responsible for assigning the workload to a specific CPU or a specific GPU or a specific FPGA or whatever execution environment is available there, provide also the virtualization platform, and actually execute it. So we currently have 2 levels of scheduling at different granularities. But in BRAINE, in the project, we anticipate to have a set of or a group of, or sometimes we call it a federation of clusters. So there should be also some mechanisms that this federation works together, or is possible to submit a job to a cluster and then the cluster decide about the node and also about the CPU. So we are thinking of having a higher level scheduling, that is scheduling or distributing workloads between the clusters. So for this purpose, we have this kind of single or multiple federation manager model. In this case, we have a federation manager, let's say federation manager 1, and then clusters are members. Some of the clusters are member of this federation, some of the clusters are member of another federation. Let's say, for example, here cluster 1, 2, and 3 are members of federation 1, and at the same time cluster 2, 3, and 4 are the member of federation number 2. So in this case, cluster 2 has a dual membership with federation 1 and also with federation 2. The reason why we are thinking of multiple federations is that to first of all avoid central management by federations, and second is that we anticipate that different federations may have different policies. Let's say, for example, different scheduling algorithms, different pricing models if it happens later. We don't think about the pricing model for now, but it happens that policies go to pricing, policies go to enterprises. If there is a multi-tenant system, there should be or can be different policies toward different tenants and so on. So we are not trying to have a single federation that is controlling all the clusters. It's just that clusters register themselves to be member of different federations, and then the federations have their own policies, where based on those policies, they will distribute the workload. So in this case, there are 2 other alternatives, or let's say variants, that we are thinking of. First is that there is a federation workload exchange. Let's say if a workload number 1 coming to federation 1, and federation 1 think that it is not possible to execute it under the terms of this federation, it may ship it to federation 2, and then it will be queued up on federation 2 for execution later based on the policies of federation 2. Another scenario is that if, let's say, for example, cluster 4 here is running this small workload, and then for any reason it decides to terminate it, there is a way to push back to the cluster. Let's say in this case, cluster 4 decides that I'm not able to execute this workload anymore, so it will push it back to the federation. It will go to the federation queue, and then is the federation manager to decide whether it wants to completely terminate it, or it wants to schedule it for another cluster, or even it wants to pass it forward to another federation to be executed under the term of that new federation. So, but in terms of scheduling itself, here you see that we also have L2 scheduler. So we had L0, L1, and L2 schedulers at different levels. Now I'm just talking about the scheduling at L1 level, that is the core Kubernetes scheduling. Inside Kubernetes scheduling, there are multiple phases of workload processing. So 3 of them that we are interested in is this sort here, and then this filter here, and then score here. So with filtering, with sorting, sorry, the Kubernetes decides who should get scheduled first. So if there is a queue behind this sorting mechanism, the sort algorithm decides which of those queued up workloads should be scheduled or sent for the scheduling. So in this case, actually, with a standard Kubernetes, it's a FIFO queue. We want to make it multi-priority queue and have single or multiple optimization objective on that. So for this purpose, we are working on a reinforcement learning to replace the standard algorithm here and have machine learning, reinforcement learning here so that we can automatically classify the workload, give them some sort of indexing, and then based on that indexing, we choose the one that we think that is the best to be scheduled next. So this is one place that we actually inject or integrate machine learning into the infrastructure itself. The second part here is with filtering. Filtering basically means that we will check if a workload can be placed at all. So this can happen, for example, if the resources that are requested by the workload are not currently available. In that case, placement is not possible. So resource-related filtering is one of the reasons. Second is that policies can prevent a workload to be placed. Let's say, for example, you are asking for a SLA of response time of 2 milliseconds, and we are not able to guarantee that, so we won't place that workload and we don't accept it. And the third item is that it's possible to look at the previous or historical behavior of the workload and based on that conclude whether this is a safe or good option to be placed. So again, here we are looking at predictive modeling so that we can somehow predict whether it makes sense to place this workload. And if not, we just reject the workload. If yes, we push it forward for scoring. And then as you guess, scoring is basically matching the requirements of the workload with the availability of the resources on the cluster. So if you are asking for 2 GPUs, for example, and we don't have it, then we are not able to to place you. And if you are asking for 2 CPUs, but we have multiple nodes that have more than 2 CPUs, then which one is the best for you? This is also a strategy. So we need here some sort of matching, which is called a scoring, and also a strategy to choose between those who match. So here again, we are working on machine learning algorithms, especially reinforcement learning, to learn about that and assign a queue index to each of the workloads that are that have made it to the scoring step. And then based on that, we choose for each workload the highest queue index node that has actually matched with that, and then we pass it for the binding that is not in this slide. So when we have this machine learning components, they are basically building models. So let's say, for example, these are different EMDCs that their internal scheduler is using machine learning to place the workload. So they are learning individually inside their clusters. So one thing that we are also doing here is that to make them share their models only, so the models that they are learning over time, they share it with, let's say, one of the federation members. The federation members makes an aggregation of those local models and send back an aggregated ML model, so that it means that each cluster is indirectly learning from other clusters how to place the jobs. So in a long run, it means that they are contributing to the federated learning and they are also learning from each other. So it's like a win-win strategy for all the members. So that was about the work placement. Now I will switch to telemetry framework and a little bit on the monitoring that is associated with the telemetry framework. So in general, if you remember from the hardware and from the layers here, sorry for this kind of problem with the font size here. I didn't see it previously. So we have the network. On the network, we have the network hardware and also an operating system here. And then on each of the node of the cluster, we can have hardware, we have operating system, and we have virtualization platform. And then on top with that, green boxes, if you see, they are the workload. So at each layer, we will collect some metrics, like for example, from the hardware of the network, from operating system of the network, from operating system and virtualization platform, and also from the applications. We collect some metrics. We have a long list of metrics, either standard metrics and use case specific metrics. So, and one of the tasks of the partner is that actually to plug that into the whole architecture. These items or these metrics will be sent to a telemetry component here that you see. We have a scraper that is actually ingesting data from the nodes and from the network. It will store it in a database, and then database is connected to 3 other components. One of them is an emitter. This emitter is basically providing querying capability so that other components can query the database. And those queries are mainly, let's say, time-sensitive data, because this is a time series a stream of metrics that are coming in. So, for example, here the dashboard will ask for a lot of data based on time, like 5-minute window aggregated of this and that and so on. And then we also have, let me find my mouse, the alerting component here is actually a CEP, complex event processing, that is continuously monitoring the database and querying the database based on the definition of the alerts. And then if there is a match, it will create an alert, and then that alert will create some sort of notification. Those notifications can be passed through people or other machines to take actions. But here in this architecture, we have 2-3 considerations. One is that the technology stack that we use is based on Prometheus. So the scraper here is Prometheus. The database is going to be InfluxDB. The dashboard is Grafana. And then the alerting is also the Prometheus Alert Manager. And the emitter is Prometheus query language that is called PromQL. So all of them work together completely properly. The only issue that we have with Prometheus is that Prometheus is a pool-based system, which is very good for scaling out, and also it satisfies almost all the requirements. But in some, let's say, boundary cases, we have applications that their lifetime is shorter than the scraping time interval. Let's say, for example, if a scraping time interval is 10 seconds, there can be an application that is live only for 8 seconds. So it has no choice or no chance actually to push the data to the scraper. That's one scenario. Another scenario is that in some cases, we have high resolution metric generator components. So they generate a lot of metric values per scraping interval, but the scraper actually ingests only the last item there. So we are losing resolution on that. So for this 2 purpose, we have this messaging queue in the middle as a pop-stop mechanism. So all of the collectors here will actually push at their speed to the messaging queue. And then the messaging queue has an additional component here on top that will be waiting for the scraper to do the scraping at its own pace. So in this case, we don't lose data. And also those short-lived applications have the chance to emit their collected metrics. At the same time, here with this bypass, there is a chance for us to inject high-resolution metrics if the scraper is not able to ingest them. So we will do them with this cherry inserting directly into the database in the format that is identical to the scraper format and a standard. So basically the emitter on top and dashboard and alerting components will not notice the difference. So again, back to the layered architecture. Here I have 2 or 3 slides on the use cases. Use case 1 and use case 2 have a lot of AI and machine learning in them. So I'm trying just to explain how they are integrated into the whole system. So, but before that, you realize that in layer 2 with the hardware here, we have GPU modules and a lot of other AI-ready hardware components. In layer 3, here, our work placement is not only by itself machine learning based scheduling, but also is aware of GPUs that are available in the nodes and the amount of these GPUs and how to access them. So it's able to assign, let's say, AI intensive workloads to proper nodes on the hardware. So we hope for a better utilization of those GPUs over time, but this is something we have to test. And then on layer 5 here, this use case 1 is going to build a digital twin for patient data analysis. And the second one, use case 2, is going to have an incident detection in video streams. So let's take a look at them. Here with hospital system, the idea is that to have a large number of patients that are equipped with real-time or near real-time sensors in their household or on their body, or if they are in a hospital, then in their hospital and so on, which is streaming the important vital signs to a central place in the hospital. And then that stream of vital signs is augmented with databases of diagnoses, therapies, backgrounds, and so on. And then based on this, on the EMDC, for each patient, there would be a digital twin. And this digital twin, because of the privacy issues and so on, must be completely isolated from others. So it's not possible to create, for example, a single database and put all the patients' information there. So each patient, the full stack of digital twin of patient, from file system, from database, from application, and from all the resources that are assigned to that digital twin, must be isolated from each other. So in this case, the idea is that to have this digital twin, and based on that, try to have patient status identification, whether it's healthy, whether it's in danger, whether something is happening there. And then based on that, to rank those statuses. And if there is something abnormal there, it will try to alert or start triggering to take action. So in this case, for patient status identification and ranking, there would be machine learning also here, which means that we have workloads that demand for machine learning and AI. And then it goes to the work placement component, and work placement should be aware of this kind of requirements and place this kind of workloads properly on the nodes that have enough, let's say, GPUs or other type of accelerators available. The second one here, a smart city that is processing huge number of video and audio streams, as you see here. The pipeline is that the data is coming from microphones and cameras. They go to data stream collectors. Some pre-processing is happening, and then data fusion is happening. Let's say, for example, multiple cameras are looking at the same place from different angles. So here, data fusion should actually recognize those, try to merge them into some sort of holistic video stream, and then the video stream goes to the analytics service. So here there are some examples by crowd estimation. For example, here in this picture, bottom left, there is emergency detection if something is happening, and some near real-time reaction should be taken. Noise analysis to understand what is going on there in the environment. Face blurring for privacy issues. Let's say you are looking at the car, trying to detect the number plate, but there are passengers there, or there are some pedestrians around. So face blurring should happen before the actual analysis, because actual analysis has been requested by a tenant that has no permission to access the faces of the people. So this kind of multi-tenancy actually goes deep into the pipeline of the process, or even the flow of the processes and so on. So these are the two examples that I wanted just to share with you as an introduction, or as a, let's say, as a clue, how this EMDC and how the hardware is going to be exploited by AI intensive workloads that are not only consuming a lot of data, but also producing a lot of data. So by this, I guess I am done with the presentation. Give back mic to Peter, and thank you, everybody.
Thank you for the presentation, Javad. And now we can move on to the panel session. We don't have too many questions. Janusz, do you see the
Yes.
questions? Okay.
Actually, I prepared one slide because there was an upcoming question. So if you give me the right, I give you a slide.
Definitely, sure.
Yeah. Welcome back, everyone. So the question was that why not COM HPC? And COM HPC is a new standard. So actually COM Express will be extended, let's say, in this way with COM HPC. And it's a really nice platform because it's exceeding the performance of the standard COM Express modules. For example, it will have native 100G interface, and it's manifesting in the replacement of the good old COM Express connector. So actually that's how they can reach. And actually there are two form factors. One is the COM HPC client and the COM HPC server. And of course we would target for in this BRAINE project for the COM HPC server modules, which has two sizes. And if we take into consideration the smallest size, which is 160 by 160 millimeters, actually that's what we were targeting, let's say in theory. And I found a picture. So actually the size of the board, this 160 by 100 is compared to the one we have at the moment. You see it's significantly bigger. Yeah.
Did you plan to share your screen?
Yeah, of course.
Then do it.
Yeah, thank you very much. I will do so. Share screen. Hold on. Do you see it now?
Yep.
Okay, so this is the module size we are currently using, and COM HPC is the smallest server is like this, which is quite nice, and I really like this form factor. The problem is actually there are two problems. One is the size. So at the moment we have more or less a strict requirement. Who defined it? It's a question, but we have an internal requirement that we should fit into 3U. And as you see, it's almost impossible. It's actually impossible to treat a system similar to our system with the same orientation and these kind of things to a 3U system. So actually 4U would be required. So the 3U limit is 133 millimeters. We are having at the moment 116 millimeter heights, but also the backplane and all these kind of things require space. So 160 and 160 would extend the height to 4U. And also there is another thing I just put height, but it should be like pitch, that at the moment we are using between the cards, not taking into consideration the monoblock, only 2.5 centimeters or 24 millimeters. And this COM Express standard in general, as you see on the picture, is defining servers with actually 4 DIMMs, but they are DIMM memories. So it means that the DIMM memories are standing, and the height of the DIMM in general is 31 millimeter, which would expect or which would extend the pitch of our system to 45 millimeters in able to fit this. On the chat, I have seen that you shared a lot of trans modules. We are quite aware of them, and we talk with the Mr. Trans as well from time to time, like last embedded word when it was introduced. But actually this would increase the pitch as well. And don't forget that from computing point of view, this would be really nice to use because it has better CPUs available. But all other platforms like the GPU, they won't eat up this space, also the storage and the FPGA. So actually we would have some space in the air that is not used for anything. And you know, our biggest dream is that to put as much computing as possible in a 3U rack, and it's not that much affordable that the volume is not used. And you know, in usually why it's not happening because of the cooling, but we have such cooling that can take away the heat that as we wish. So if we talk about the volume, the current solution compared to the COM HPC size D, it has an increased volume of 7.3%. So it's, as you say, it's not negligible that the volume that we use for the processing module is increased by 7 in the COM HPC size D platform. So these are the maps that we made like 6 or 8 months ago when we designed the architecture and the connector. And there is one more thing that really the Xeon processors, so not like normal processors, they will use DIMM memories, and the DIMM memories are standing, so there is not easy to implement the cooling for the DIMMs because they will be standing. So that's also another problem. Some modules like the FPGA that you shared, they use a SODIMM, so they are laying down, so it's easier to cool, and also maybe the pitch is better. But in general, these were the consideration when we said that, yeah, guys, let's go for ComExpress Type 7. And as you pointed out, it's really nice that actually the interface is the same. So if we redesign the backplane and we have a new mechanics, it should work actually. But we had to stick to something. And at the moment, the ComExpress size is the basic size with 95 by 125 looked the most logic, and also matching the GPU size and all these things. So
is there any chance that the PCI Gen 5 will also be implemented in ComExpress 7 or not?
On ComExpress 7, no, but you know, Gen 4 switches were introduced to the market last March, so it's not, you know, the specification is quite ahead, but PCI Gen 5 is not in the market for normal computers either. So it's specified, it's nice. Actually, our connectors can support it because they are specified for that rate, but in general, it's impossible to build now a system that you want to build and demonstrate with Gen 5 because actually none of them is supporting. In general, ComExpress is specifying Gen 3 interfaces, but for example, the GPU will have Gen 4 interface, so we will use heavily that one. And the connector itself, it's a shame. So I know it's a shame. We have other projects where we are fighting with this, but for example, the LX2160 SOM module from SolidRun, they already have 100G interface on the standard ComExpress connector. So it's not impossible, but you have to take special consideration. So at the moment, it's okay.
I think also maybe as a conclusion to say about this is we try to build a system that integrates a lot of various different innovations in the cooling, in the whole architecture, in the software, etc. And we try to build a system that at some point can simply be adopted by the market. So the complex system as a whole needs to have a high enough TRL level in order to be taken up to the market. And otherwise, this project is just a beautiful project, but nobody will use it because there's no appetite for it in the market. So I think that boils down to many of the decisions that we've been making over the past couple of months. Are there any other more questions, maybe, or not?
There's a follow-up question. Are you sure that ComExpress Type 7 connector will do Gen 4?
So actually, it's this is not exactly what I stated. So the connector that we choose for BRAINE, it's a TE sliver connector, and it's specified for 56 gigabits per second. So Gen 4 and maybe Gen 5, once it's appearing, will be okay. the COM-Express connectors, they are suffering with Gen 4, and actually there is no COM-Express modules at the moment on the market with Gen 4 interface, only the GPU, but they have a SAM-TAC-SAM connector. But answering to your question, there will be introducing this year, the first 2 quarters of this year, COM-Express modules with Gen 4 interface. I know some suppliers, they are already releasing this to the production. But actually the standard COM-Express connector was redesigned by T and also some other manufacturers to improve the signal integrity. They look like the same, their connection is the same, so it's compatible, but the performance was increased. So Gen 4 is available with the same connectors. Not now, there is no CPU to support, but in the close future there will be. And we are ready for that.
Yeah. Let's check if there's some more questions. I don't know, there's enough participants in the presentation, so I don't know who is raising a hand. Not at the moment.
So we encourage participants to have questions, so please feel free to ask anything related to BRAINE.
Maybe a question to the panel as such, and I think it's maybe a hard one to answer. So I've been talking to some of the 5G telcos, and lately I was also in a conference for hospitals, and they were saying, oh, we need an edge infrastructure, but we can't afford it. So there is kind of a, even though we try to build a grow as you go model, somehow we're looking for the spots in the industry where the grow as you go model actually can kickstart the building of edge infrastructure. Smart cities are struggling. So where do you think, which industries or which verticals do you believe have an appetite or have a need to kickstart this? I'm asking the panel members, Sean, Janusz, Javad, Peter.
So my first understanding would be that what are our highlighted features? Based on that, we can match it with the requirements of those niche markets, let's say. And one of the most important ones for me is that this privacy ability in the form factor. So it's like a physical privacy, and also is a logical privacy, logical by software and so on, and physical by the owning of the device and having it somewhere in your facility. Like if you have a hospital, I'm also looking at police stations, for example, stadiums and so on. So those who need to process a lot of data, but they have a lot of privacy issues, and they want to get a certificate from, let's say, authorities that, hey, we are using this device is using this standard, complies with this standard. So we are good to go with that. Yeah. So this can be one possible pathway.
Yeah. I had a conversation with the dairy industry in New Zealand last year. They're very well organized, the farmers and the production facilities, the factories. And they are looking at creating this private cloud with their own infrastructure spread out over farms and factories. And they have also the money to invest in something like that. And I think with these kind of arguments of, privacy protecting, federated learning, the farmers can learn from each other. You can have AI engines running on the various farms. And since they're more or less doing similar things, the AI engines can learn from each other. And at the same time, the factory is well aware of what is coming in terms of produce towards their factories. Sean, what do you think? I mean, you as Dell have you guys are very well, you know what's going on in the market. Can you lift a tip of,
Yeah, I'm not sure where I would start. What I would say, I guess, yeah, for the BRAINE platform, I kind of the advantage it provides, I think, yeah, one of the key markets where this type of platform could succeed is in the telco market, as you mentioned. And for a lot of the reasons that Javad just described, the telco market, obviously they want to be in Edge. It's a big market for them. It's the infrastructure, especially in the infrastructure side of things. The issue is a lot of the traditional Edge deployment systems, are based on a centralized or a cloud style hierarchy. And then if the telcos wanted to adopt, say a Google type model or a Azure or AWS or whatever, the problem is that they're very much under the influence of the hyperscaler, and they don't have full ownership of the services or the data that they're running at the edge, and they don't want that. So what we're looking at in BRAINE as a whole, and what Dell would like to provide to telco companies is a platform that a platform that's at the edge, that's fully independent and that they have full ownership of and can control entirely by themselves. And if obviously there's some big features like I might have undersold it at the start, but cross-platform compatibility with x86 ARM FPGAs, that's obviously a big component of this project. And if we can achieve it and have a solution that works, then I think it's something that would be of huge interest to the telcos, and it could very much cause a big change in the industry going forward.
I see the market, the telco market, I had some conversations there. I see huge, let's say, strategic pressure. So for example, in the US, there's quite a few, let's say, startups who try to push something like that, like an elastic edge into, in a 5G infrastructure. And telcos simply refuse to work with them. They want to develop their own stuff. And similar here in Europe, I know a little bit of what the hardware that's being developed at a few of those, at Ericsson and Nokia, and it comes nowhere near to what we are developing, but still they are not ready for it. There's not enough pressure for them to start collaborating on this level. Maybe Rakuten in Japan, they're creating a completely open system to compete on the 5G market together with NEC. So maybe they're interested to do something, and maybe in Europe, who knows?
Yeah, I think it'll be interesting to see how it develops going forward. Unfortunately, I don't have a crystal ball available to see how it will end up.
Yeah.
But, I think the platform we're developing, it can be very compelling to the type of markets like telcos.
Yeah, I know that car industry like BMW and Mercedes are also building their own data centers on premise. In Germany, probably also to pull a lot of data towards their their own locations and to process it there instead of processing too much on third-party infrastructure. So the whole idea of what I find fascinating is that even though you don't give them access to the raw data, simply processing your raw data on somebody else's infrastructure could give them already so much information that they know a lot about your process and your whole approach, etc. So I think slowly that awareness is coming in the industry. So I think it's just a matter of time, and who knows, maybe next year or in 2 years we will be able to mention some wins in those areas. Do you guys have any questions, guys, to the panel as such, and that are maybe interesting for the audience?
Javad, you are muted.
One possible question that I would like to have an answer for that, possibly is too early, but if you are thinking of mass production of this EMDCs, what would be your imagination of the pricing?
Yeah.
Let's say if I am a factory owner and I want just like, let's say, tens of these devices.
Yeah. Well, to give you an idea, I mean, we're still looking at pricing. We're now building prototypes, and so I think in a year time, we will be able to understand what is the exact price of the whole solution, and what kind of discounts are we getting if we start producing in volume. But I did kind of a rough estimate, and for example, I tried to build a system that is performing better, and that was a couple of months ago, better than the DGX2 system of NVIDIA. And be aware that's a typical GPU system, so it's not as heterogeneous as ours. But I thought let's populate it in a similar way that DGX2 and NVIDIA populated it. I think they sell that system at the time, I think for 400,000 or 500,000 euros. And I think the cost of our system, as I calculated then, with the rough numbers that I had, came down on 250,000 euros. I mean, it's a Google the specs of the DGX2. It's a massive system, and our system had many more cores, much more energy efficiency, etc., much more memory. But that gives you an idea of what the margins are that big players like NVIDIA are doing. And of course, they have a software platform running on top. They have a whole ecosystem. But yeah, there's a big margin to play with, and that gives you a little bit of an idea of what the price range is. That's of course for a 6U system. Yeah, that's 2 times 3U. Once you start breaking it down into, okay, we have a, I don't know, 24U system or 16 or 8, of course that price comes down.
Good.
What do you think of that pricing?
But actually, I'm not running a business, but I personally expected lower price.
Okay. So but you would buy a DGX system for 500,000 euros or not?
Not sure, no. No, I mean, if I'm looking at the processing power there and translate it to, for example, to the equivalent for AWS for 10 years, let's say, they should match each other. So when I'm renting AWS cores, I have no other cost to pay for. Let's say no place, no fuel, no electricity, no permissions from authorities if I'm consuming a lot and so on. So I'm just paying for the AWS service. And then at the same time, when I'm owning this infrastructure, I should also think about its lifetime. So is it like for 5-year investment, 10 years investment, 20 years investment? And then based on that, there should be a point that they actually reach to each other that is 0 point. So I have to see my benefit from that let's say this investment will come back in 2 years or in 3 years or in 5 years, comparing to the same processing power when I am on Amazon.
I will send you an interesting paper that I found 3 days ago. It was, I think, a German university that analyzed exactly that. So what if I get it from AWS, or I have the NVIDIA Xavier and my own system, and I'm running workloads on there. And they looked at all the costs. So, if I have my own system on premise, people, cooling, infrastructure, and AWS, and it very much depends on the type of workloads. So if you have high utilization, and that's what we're aiming for, so a lot of data in one location, a lot of analytics and a lot of AI running, then you absolutely, it is far less costly to do it on premise with lots of other advantages as well, privacy, etc., than doing it in AWS. But if you just do a little bit of AI, of course, then doing it in AWS it's much cheaper.
Okay, sure.
But
so
also,
it means that you should have a serious utilization, a serious application.
Yeah, but I mean, I submitted a proposal a couple of months back with a number of hospitals that wanted to have those systems. They're also buying DGX2s, and they wanted to have systems on premise to do federated learning for rare diseases and cardiovascular things. And they believe they have the data and the utilization levels that justify for an on-premise infrastructure. So I think the use cases are there. They're still thin, but I think with a little bit of work, they become more and more and more. Let's be honest. The AI,
Sure.
at the edge will grow, as you saw in the picture that I showed you. It's a $5 billion market in 2025. So
Great. So maybe just for our project, it would be good to add this financial aspect to one of this panel series also.
Yeah.
For the next year.
Yeah, I think that would be then not this year, but the panels in next year.
Yeah. So this year is already booked.
Yeah, and also then we would have enough data, because then we can actually, then we have a system, we can run some workloads, and then we can run those workloads also on AWS and on Google.
Right.
Maybe find a page. Maybe we can approach the same PhD or the same professor that did the analysis in the report that I will send you. Maybe we can ask them to do it again and then use our system and see what happens. Yeah?
Yeah, very good idea.
I think Dell will be also interested in that, right, Son?
Yeah, absolutely.
All right, cool, guys.
Just one thing I'll mention briefly, just to the attendees, just in case they don't know about the structure of Horizon 2020 projects. So because this is a Horizon 2020 project, all the deliverables we'll be making will be published online for free to access. So if you are interested in what we've been developing in the project and you want to read up on it, we'll be publishing deliverables on the progress, on the progress of the software and the hardware as the project goes on, which you can find on the website.
Yep. And yeah, people who are interested can always reach out to us. Go to the website of BRAINE and or find us on LinkedIn and send us a link and then talk to us.
Absolutely.
Yeah. I think that's I don't know. Peter, you're moderating.
Yep. Are there any further questions from the audience or from you guys? If not, then I would like to thanks everyone for attending. Thank you for the great presentations, and we will meet tomorrow.
Okay. Hope we can meet each other in person soon.
In person, yeah, that would be great.
Thanks, everyone. Bye-bye.
Okay, guys.
Thank you, everyone. Bye-bye.
Bye-bye.
Bye.